and Claudia. Yeah, we're all here, the 6 members of the committee. And actually, due to the COVID-19, the seminar series has been held online weekly and since August of 2020. It aims to present and discuss recent developments and the future direction on both theoretical and experimental sides related to heavy ion collisions at RHIC beam scan energies. And in the last year, we have successfully complete the RHIC beam scan seminar series 3, actually, which has found a phase 4 falling with well over 100 regular participants every week, and sometimes more than 200. So here, and on behalf of the organizing committee, I'd like to announce the 4th seminar series on RHIC beam scan get started today. And we actually feel very happy and honored that our first talk is featured by Professor Frank Wilczek. And he will talk about the actions from deep QCD and to cosmology and new search strategy. And we also have very happy to have Professor Willy Hans. He has kindly agreed to chair the seminar. So now I'd like to hand the time to Willy. Yeah, please.
All right. Yeah. So good morning, good afternoon, good evening. Welcome everybody. We promised Frank 60 minutes, so I will keep this brief here. According to his website, Frank Wilczek is a theoretical physicist, chromotechnologist, intellectual adventurer, and author. In 1973, he announced his arrival on the physics scene with a PhD thesis on asymptotic freedom in non-abelian gauge theories, which ultimately won him the Nobel Prize. In 1977, he studied the Petrie-Quinn solution of the strong CP problem and showed that the spontaneous breaking of the Petrie-Quinn symmetry results in a new particle, the axion, which is the subject of today's seminar. In 1982, he introduced the name anyons for quasi-particles in two-dimensional quantum field theories that are neither bosons nor fermions, and then he later showed them to play a key role in the fractional quantum Hall effect discovered in the same year. Frank invented time crystals in 2012, and in a continuous stream of path-breaking work, he made fundamental contributions to particle physics, nuclear physics, where he and colleagues discovered color flavor locking and the color superconductivity in QCD matter at high density and low temperature. And he also clarified the phase transition, the chiral phase transition in QCD and the critical point in the phase diagram to condensed matter physics, including the condensed matter physics of QCD, and much, much more. He won the MacArthur Genius Award in 1982, the Dirac Medal, the Julius Edgar Lilienfeld Prize, King Faisal Prize, and of course, the Nobel Prize, which he shared with David Gross and David Politzer. And he's a member of the National Academy of Science. He has written many popular books and popular science columns, which all shine with the exceptional clarity of his thought and language. And we are thrilled to have him here in our seminar today and looking forward to to his presentation. And before I hand over the word, the ground rules are, please, if you have questions, please type them in the chat. I will monitor the chat. If the question is something that should be urgently responded to so that the talk stays continuous, I will interrupt Frank, but otherwise I will collect those questions for the question and answer session at the end. So Frank, now you are ready to go.
Okay. Thank you very much for that very flattering introduction. And let me share my screen in the appropriate way. There. So I hope you see a blank white screen. Is that right? And
we do.
Okay. So thank you again, Yuli, for that lovely introduction. And it's a great pleasure to be talking across continents and have such a lively audience. I will be talking today about something that is a little to the side of heavy ion physics, but it has a common source in the deep structure of QCD, and there certainly are aspects of it that get illuminated by heavy ion physics. I'm looking very much forward to the results from recent experiments at RHIC that will elucidate the phase diagram, but we don't have them yet. What I've actually been working on that's mostly related to QCD and the intellectual problems that arise from it in recent times is axions, and in particular trying to finally observe the darn particles. And I think we're making very significant progress on that, and I'd like to share that with you. But since not everyone has been with the subject as long as I have, or paying as much attention as I have, maybe it makes sense, given that we have people with different background and people trained in experiment mostly, to start more or less from scratch. And I will be able to start from scratch and give you at least a highlight introduction to several of the outstanding features of the landscape around axions. There's a lot I won't be able to cover, so let me give you, in this outline, also have mentioned very briefly some items that are in parentheses here that I won't talk about. So first, I'll discuss why fundamental physics needs axions. Then I'll discuss what axions are in the language of particle physics, and especially their electromagnetic interactions, which are interesting and the basis of many experimental searches that I'll want to discuss. Then I'll discuss an unexpected gift from the early days of axion physics, which is that axions can also, although this wasn't what they were originally designed for, they also may very well provide the dark matter that cosmologists need. There's a lot to say about axions and astrophysics. Astrophysical sources, especially neutron star environments, also black holes, can be useful probes of axion physics, but I won't have time to discuss that. There are a number of laboratory axion inspired or axion constrained experiments that look for long range forces and other things in the laboratory. But again, I won't be able to talk about those. I will talk, however, about attempts to actually observe the axions if they're the dark matter. These are called haloscopes in general. The haloscope means something designed to discuss observe the dark matter halo in which we're embedded. And I'll discuss in particular a new idea that we've been very, very actively pursuing and looks extremely promising, called the plasma haloscope. And then I'll only mention in passing what's become a thriving industry in condensed matter physics. That is what I call emergent axions. These are collective excitations inside matter that obey the equations of axions, of course, with different interpretations of what the symbols in the equations mean, but they have very characteristic physics, which is shared by axions, but by fundamental axions, and they display it in a much more accessible context. And this has become, as I said, a thriving discipline within condensed matter physics, with actual data as well as nice ideas. Okay, so without further ado, yes, as I said, I won't be able to talk about all these things, and all of them except the emergent stuff can be is contained with, I think, hundreds, maybe over 1,000 references in some standard review articles. Okay, so quickly, why does fundamental physics need axions? And this is brought forth in a very understandable and dramatic way through a series of why questions. The time reversal symmetry of the basic equations of physics has been a strange but notable property of the fundamental laws of physics for several centuries, starting with Newtonian mechanics, where basically you have accelerations related to position-dependent forces, and since accelerations are quadratic in times, when you reverse the sign of the time, you get the same equations. But if you imagine running the solar system backwards in time, it still obeys the Newtonian celestial mechanics. And that strange property, which is certainly not necessary to describe experience, ordinary experience is anything but time reversal symmetric, and we remember the past but only guess about the future, for instance. That strange property continued through general relativity and quantum mechanics as physics evolved, included more and more phenomena. This strange property remained in the fundamental equations. Why? As long as it appeared to be an exact fundamental feature, it was unclear that asking why would be fruitful. Sometimes, if you have a beautiful principle, that's just the way it is. That's rock bottom, and can't be explained in terms of anything simpler or more beautiful. And time reversal symmetry might have been in that category. But the situation changed in 1964 at Brookhaven, actually, when Jim Cronin, Val Fitch, and their collaborators discovered a subtle effect in K-meson decays that slightly violates T. Actually, what they discovered was a violation of CP symmetry, charge conjugation times spatial parity. But there are very good reasons to think that CPT is a precise symmetry, and so violation of CP is equivalent to violation of T. And subsequently, actual T violation has been observed in other experiments. So T symmetry is definitely not rock bottom. It's not even quite true. And that makes it even more puzzling. Why is it approximately but not exactly true? And remarkably, we've almost nailed it. We've almost solved this ancient problem at the foundations of physics in the following way. It turns out that the basic, I'll say, sacred principles of modern physics, relativity plus quantum mechanics plus the local symmetry that underpins the standard model, are very powerful when they act together. Now, I put sacred in quotation marks. Of course, this is science, not religion, and in principle, nothing is a sacred principle. But these concepts of relativity, quantum mechanics, and local symmetry explain so much and appear to be so profound that we would have a lot to unlearn if we found that they were violated. And they certainly seem to be more profound and therefore a basis for discussion of time reversal symmetry as a consequence of that. So we would be happy if we explain time reversal symmetry based on these more fundamental principles. And acting together in the framework of relativistic quantum field theory, they constrain the possible interactions very powerfully. And in fact, when you analyze it, you find that in the standard model, there are exactly two possible sources of T-violation. One of them, discovered and elucidated by Kobayashi and Maskawa, beautifully explains what Cronin and Fitch observed in K-mesons and a lot more in weak decays of heavy quarks, especially. But the second possibility, the second consistent interaction doesn't happen. Here I elaborate a bit on what the interactions are, but in view of the limited time, I won't, and since this is probably well known to this audience, I won't belabor this. And it's kind of a side issue for what follows. The CKM phenomenology of T-violation works very well. The other term, the one that doesn't happen, is something that's intrinsic to QCD. It's a coupling of gluon fields to each other in the form of an electric times magnetic dot product. This self-interaction of colored gluons is non-trivial in the quantum theory of chromodynamics, even though in the classical theory, it's formally a total derivative. So it's a deep property of quantum field theory that this interaction has non-trivial effects, but we know, for instance, that if it didn't, then the eta meson would be, or eta prime meson would be much lighter than it is. So this interaction, both theoretically and sort of numerically and experimentally, is a necessary component of QCD, or the fact that E dot B interaction fluctuations affect the behavior of gluons. However, this term as a fundamental interaction as opposed to a fluctuation is very dangerous because it changes sign under time reversal. So a non-zero angle of the theta parameter here, the non-zero value of this coefficient, would break time reversal symmetry within QCD. And this doesn't involve heavy quarks or any exotic weak interactions. This is just hardcore QCD. And so a non-zero value of theta feeds more or less directly into the electric dipole moment of the neutron, a famous T-violating effect. And the only thing that keeps it small in the world is, in fact, the fact that it violates T-symmetry. So the experimental limits on the neutron electric dipole moment have been improved over the years. It's been a major enterprise of experimental physics to try to measure this electric dipole moment, but so far the results are all negative, and interpreted in terms of the theta parameter, they limit its possible values to less than a part in 10 billion. Why? So now we have a numerical coincidence or numerical fact that's very impressive quantitatively. And to me, it's much too tight to be explained away as a coincidence. Over the past, so that's sometimes called the strong CP problem or the strong T problem, or just the theta problem. Over the past 40 plus years now, since these aspects of QCD were first properly understood, there have been several attempts to explain why theta is so small, but only one has survived detailed scrutiny and stood the test of time. What we do, and I'll fill in a little bit more of the technical details momentarily. What we do is promote the unwanted coupling constant, that theta, which within the standard model itself is just a number. We promote it to a dynamical entity, a field, something that can change in time. So instead of a number, instead of a coupling constant, theta within an expanded version of the standard model becomes a field. And if you set things up right with the appropriate kind of symmetry, the so-called Peccei-Quinn symmetry, then this dynamical entity, that you add to the standard model, wants to evolve to zero, wants to evolve to a value wants to settle down to a value that's very nearly zero, a value at which time reversal symmetry is very well maintained. Not exactly, but very, very well. This then would explain the otherwise mysterious coincidence. It's a remarkable concept because it really brings the idea of evolution of what on the face of it seems like a constant of nature into physics. So it's a theory of evolution now, not for animal species, but for the constants of nature. Here's a picture of it that I like. So back in the early universe, you have a field that starts out in some excited states, but as the universe cools and expands, it can lose energy and spiral down to its minimum energy, which is attained when the effective value of the theta parameter is very nearly zero. Now, to implement this idea, we had to introduce a new quantum field. The theta parameter became a field, and that field, like all quantum fields, creates particles. The electromagnetic field creates photons. The electron field produces pions and photons and electrons and positrons and so forth. Those are the basic ingredients of our picture of the world. And this new field is no exception. When you apply the principles of quantum mechanics to it, you find that it makes a particle, and the particle I call the axion, inspired by a laundry detergent because it cleans up a problem. And well, this is actually how the name arose. Okay, let's go through this a little more technically. So the standard model divides into two sectors, the gauge sector and the flavor or Higgs sector. The gauge sector is tightly principled and brilliantly successful. The flavor sector is much looser. It's been very successful in correlating data, about organizing data about the masses of different quarks and which one decays into the other, and similarly for leptons. But it has many phenomenological input parameters. its most striking success, in fact, is the Kobayashi-Maskawa theory of T-violation, I think. And the Nobel Committee agreed with that. That's what. But as I discussed, there's a serpent in the garden. This explanation of T-violation in the world is not complete because although some of the non-zero phases are explained in terms of the Kobayashi-Maskawa scheme, the overall phase of the quark mass matrix, which is also physically meaningful, is related to this theta parameter. In fact, it's essentially the same thing if you use the so-called anomaly equation for the axial current, axial baryon number current in QCD. And as we mentioned, it's very small. So Kobayashi-Maskawa pick out some of the angles to be important, but one of them is set to zero. It seems like a very conspiratorial idea, if you think about it this way. And this, to me, is the most striking unnatural feature of the standard model. That is an unexplained numerical coincidence, aside from the very tiny value of the cosmological term or dark energy. I should say that whereas for the cosmological term, people have appealed to anthropic reasoning that if the cosmological term were much bigger, we wouldn't be around to observe it. Whatever you think of that argument, it doesn't work for the theta parameter because the theta parameter could be much, much larger than it is without significantly affecting any aspect of everyday life. So you could perfectly well have observers in a universe that had non-zero values, much larger values of theta than we have in our world. Okay, a little bit more about the actual symmetry. So you want to be able to have dynamical degrees of freedom that allow you to rotate away by field redefinitions, the phase of the quark mass matrix. And if you do that, if you look at the source of the physical source of energy dependence on theta, it comes from instantons in QCD. You can also analyze it more abstractly, but it's nice to have a picture, and then you can do that in terms of instantons. And if you have this kind of contribution to the vacuum energy with weighted by a phase, e to the I theta, and then the anti-version gets an e to the minus I theta, so it's altogether cosine. And you minimize at theta equals to zero. So you actually minimize the energy when theta equals zero, where theta here is the relative phase between two Higgs fields, one of which couples only to right-handed quarks, the other up quarks, the other of which couples only to right-handed down quarks. So that implements this idea that that you have a dynamical degree of freedom. Here it's the relative phase between these two different Higgs fields that that responds to the value of theta directly and is minimized when the effective value of that degree of freedom, that field, is close to zero. Okay. There are other ways of doing it that are even more elegant, but I won't have time to discuss that. Okay, so this is the same idea here. Phi is the relative value of the two phases. So here, so in terms of the preceding diagram, it would be phi 1 times phi 2 dagger would be an emergent degree of freedom from the two Higgs fields, and you have their relative phase phi, a relative phase field phi, the magnitude and phase, but the phase is the phase of phi 1, phi 2, and when you have an expectation value for that, you get a spontaneous breaking of the underlying symmetry, and then you get to minimize and go down to theta equals 0. But there's a residual quantum field that carries very little energy compared to the very large symmetry breaking scale F. There's one that is associated with the QCD scale, namely rotations of this instanton phase, and that gives you a degree of freedom with very small mass, and that's the axion. F, the magnitude of the condensate parameters, is the stiffness of the axion field. If you think about the kinetic energy for phi and write it in this form, you realize that the A field is now the A field's kinetic energy. When you take the gradient and square it, the F's cancel and you don't get it. But all the couplings of the axion field will occur in the form A over F. So if F is very, very large, if it's a large mass scale, the axion field will be weakly coupled, or putting it another way, the underlying field of which it's the phase oscillation is very, very stiff. Okay, and I won't be going through these technicalities, but it's important to note that they exist, that symmetry dictates the exact form of the axion coupling. So we can be pretty concrete about the properties of this particle that we predict, even though the actual data on it is very non-existent. So here come the properties. The crucial ones are the mass, the spin, and the interactions. And here we can write those things down in a convenient way. So we have an ordinary spin zero field with a non-zero mass. That's the axion. Its mass, as I said, is associated with the QCD scale, but suppressed by that stiffness of the underlying condensate from which it arose. And so the mass of the axion is lambda QCD squared, which numerically will be is of the order of 100 MeV squared, divided by F. And F, as we'll see, is something that will be 10 to the 10 GeV or greater. So will be associated with unification scales, with very much larger scales. So that will make the axion a very weakly coupled particle, a very light particle, and as I said, we can write down the theory in terms of one basic parameter, F, which governs both the mass and the couplings. Here is what the couplings look like. So there are couplings to gauge fields, and there are also couplings to leptons of a very specific form. They're all inversely proportional to F. So as the axion, as F gets larger, the axion gets lighter and more weakly coupled. There are numerical coefficients of order unity that depend on the details of the charge assignments of the different quarks and leptons under this symmetry. They're of order 1. So we have one basic parameter in the theory and then other order 1 refinements that are somewhat model dependent. The electromagnetic part is especially elegant. You can separate that part out and analyze the modifications of the Maxwell equations that you get from the presence of the axion field. This is where you find equations that it turns out also describe situations in condensed matter physics. So nature also likes these equations. And they are central to several search strategies. So let me display, oops, I wanted to display what they are. I guess I didn't. Let's see. Took away a slide that I shouldn't have. So the basic coupling is from which you can derive axion electrodynamics is the coupling of the axion to the electromagnetic field. This is what it looks like in relativistic notation. This is what it looks like in common notation. So it's axion E dot B. So it's very analogous to the coupling to gluons, which is the reason for postulating the axion in the first place. You also get a coupling of a very similar form to the electromagnetic field, E dot B. And you can just see what this gives as a modification to the Maxwell equations. It's an exercise in analytic mechanics. That's very fun to do. And this is what you get. And it has remarkable effects. What you find that in the presence of an axion field with a spatial gradient, then an external magnetic field will induce effectively a charge. On the right-hand side of this Maxwell equation is the charge as far as the electric field is concerned. That's the definition of charge. So what you have is a magnetic field in the presence of an axion gradient induces charge. You also have that a time-dependent axion field, even if it's spatially homogeneous, induces similarly in the presence of a magnetic field an effective current. And this is the basis of many, many search strategies for the axion, including the one I'll just be describing in more detail later. And then you have another contribution to the effective current, proportional spatial gradient of the axion. This gives a kind of Hall effect that an electric field, a voltage induces a magnetic field, or it induces a current. And this is something that's very much studied in the context of emergent axions in condensed matter. Okay, so we'll come back to that. These are quite wonderful equations. Let me see how I'm doing for time. Not very well. So I'll go through how axions make dark matter. I'll try to accelerate a bit. So remember this picture, the basic axion dynamics is that in the early universe, you have a field that starts out in a more or less random place, and then it spirals down as the universe evolves and cools, can take energy away from this excited field, and it settles down to its energy minimum, which is theta very close to zero, but there are small residual oscillations. They're numerically very small, much smaller than that 10 to the minus 10, which was the experimental limits. They're more like 10 to the minus 14 or 15, if I remember correctly. So they don't upset the mission of the axion to explain the phenomenological observed smallness of the theta parameter. But even though they're very small numerically, because the underlying field is so stiff, they represent quite a lot of energy. In fact, you can analyze these oscillations using the interpretation of fields as quanta, just like electromagnetic fields are made out of photons. These residual oscillations are collections of particles, and that's exactly the cosmic axion background. It turns out that if you follow through the Big Bang cosmology of this settling down of the field to its minimum, there are residual oscillations, and they correspond to a residual mass density that's roughly proportional to F, it turns out. Not exactly, but very nearly. Now, axion cosmology in detail branches into two parts. One is conventional cosmology. Okay. In conventional cosmology, the universe today samples many, many independent regions that at the time when the axion field first condensed, when the underlying scalar field, of which the axion field is the phase, first condensed. That's because as the universe gets older, the speed of light times the age of the universe, which is basically how far any observer can see in the universe, gets bigger and bigger. Or in the jargon of cosmology, you say the horizon gets bigger and bigger. Reading it the other way, in the past, the horizon was much, much smaller. And so different regions that we get to see today didn't see each other back then. So they were independent. And therefore, the initial displacement of that field in the picture of the field rolling down, the initial angular dependence, which winds up being translated into the residual oscillations around the minimum, is a random variable that we should average over, because we average over many independent samples when we look out at the sky. And that takes care of the relevant unknown parameter in the cosmology, the unknown initial condition. That was the only thing that was really uncertain. And since we're supposed to average over it when we take large samples of the universe, we can calculate what value of F, remember the density is proportional to F roughly, what value of F it takes to make the observed dark matter. And it turns out to be roughly F equals 10 to the 12th GeV. Now, as I'll flash later, there are a lot of effort has been put into searching for axions, and there are experimental constraints now from astrophysics and accelerator physics that say F has to be greater than 10 to the 10th GeV. Remember, the strength of axion coupling goes down as F increases. So as you get better constraints on the possible coupling, the F parameter gets big, that's allowed, that it gets bigger and bigger. Based on existing accelerator and astrophysical limits, you have F equals to or greater than 10 to the 10th GeV. Here you need 10 to the 12th GeV to make the dark matter. So if axions exist at all, the constraints tell you pretty much that it has to be the dark matter. So if we're going to solve the strong CP problem, is the problem of why time reversal is so good but not exact in the world, we're really pretty much forced to the idea that axions provide a lot and maybe all of the dark matter. Okay, so this is a picture of intended to illustrate that in the early universe you had many different initial values of theta that translate into many different samples of axion density that average to a calculable value. And here's a very recent, impressive attempt to translate all that into a numerical expectation for the axion mass. I should say that work in QCD, especially in lattice gauge theory, is crucial to relating the values that the parameters that appear in cosmology, F in particular, to the predicted axion mass, which is relevant for experiments, as you'll see. And so this is a very direct connection between sophisticated work in QCD and axion physics. And when you put cosmology together with the QCD, in this scenario, you get a fairly precise range of possible values for the axion mass. And we'll see why that's important momentarily. If we translate it into a frequency, which is very convenient for experimental purposes when you think about how you're going to make an antenna that tunes into the axion background, it's in the range of several tens of gigahertz. Okay, there's another possibility that in between when the condensate formed and the present day in cosmology, inflation occurred, but in view of the time, I won't say anything more about that. Except that in this scenario also, it's very hard, it's even harder actually, to avoid significant axion dark matter if axions exist at all. So whichever way you go, if axions exist, they have to be a big part of the dark matter. And then Occam's razor suggests they are essentially all of it. Okay, so now let me get to the recent exciting developments in experimental and designing antennas that seem to be capable of doing the job of detecting axions if they're there. Remember, here are the equations again, and we're going to use this term. Especially, it's the largest because it turns out that interpreted as particles, axions today are highly non-relativistic. They've cooled down through the evolution of the universe. And that means that the time rate of change, which is governed by the mass, is much larger than the spatial rate of change, which is governed by the momentum. So this is the big term, and if you want to design experiments to find axions, unless there's some very powerful reason, you gain a factor of 1,000 by focusing on this term rather than that, or that one. So that's what we do. Okay, so putting the effect of those equations into words so that we can have some intuition about it, we see that in the presence of a background magnetic field, an axion field mixes with the photon. It changes the Maxwell equation. It has the same, it appears in the same equations as the electromagnetic field and mixes with it. And if the axion field is changing with time, it can pump energy into electromagnetic fields. And the design of antennas is just trying to encourage this pumping effect and then turn axion energy into electromagnetic energy, which you can then detect by all the tricks of electromagnetic and microwave engineering. And because the intrinsic couplings are so weak, in order to get detectable effects, it's important to exploit every trick in the book, and in particular, resonance. So you want to make the pumping efficient, if you like, or you want, in particle physics language, to make the axion field convert into photons efficiently. Now, if we think about the impedance match, so to speak, or the resonance condition, we see that we're in trouble because the axion is, as I said, almost at rest in the cosmos. So it's a massive particle. The mass is small, but still not zero, and corresponds to gigahertz frequencies, as we saw. Whereas a photon has energy and momentum that are equal, so they can't match. And putting in a background magnetic field doesn't change either the energy or the momentum of the things going through it, so you're stuck. So we need to do something more in order to get the conversion to go. Previous experiments, things like the ADMX experiment, the haystack, and others with axions, have been based on giving axions momentum language. So you set up cavities or set up inhomogeneous materials that give the cosmic axions a kick and allow them to match the energy and momentum of a photon and convert resonantly. But there's a different approach. If you think about it, a different approach suggests itself, which is a photon a mass. If you give the photon a mass, then you match without giving the axion a kick, and that's advantageous because it allows you to use spatial structures. You don't have to give homogeneities that break translation invariance and give the you give the photon a mass, and then that can be something that's uniform in space and take advantage of take better advantage of the fact that the axions uniformly fit in space. So how do you give the photon a mass? That seems pretty strange, but actually there are many situations known in physics where photons get a mass. Maybe the most famous, because in particle physics closely related to the Higgs mechanism is that inside superconductors, photons have a mass, and really all of superconducting phenomenology follows that inside a superconductor, the photon becomes a massive field. But that's no good for our purposes because we want to apply large external fields to encourage the axion mixing, and superconductors don't like large magnetic fields. Another place in which photons get mass is in a plasma. That's the famous plasma mass. But ordinary plasmas made from hot gases, like the things you see in neon signs, they're not suitable because they're not a suitable environment for making sensitive measurements. They're very noisy, high temperature, and so forth. But there's another kind of plasma where you have free electrons inside metals, and in there too you get so-called plasmons, where the photon has essentially acquired a mass. In equations, it appears like the photon has acquired a mass. Unfortunately, that's not quite suitable either, because it turns out that with available metals, the plasma masses are too big. They're larger than you want for axion purposes. You kind of know this without knowing it, because a famous effect of the plasma mass in metal is that metals reflect light. Light can't get in because the photon has a mass inside, so it reflects up to the ultraviolet, and so the photon mass in a metal corresponds typically to the ultraviolet, whereas we want a mass in the gigahertz range, way down in microwaves. Semiconductors might be a better bet, where the electron is smaller, but for a variety of reasons, this hasn't really panned out yet, although we've looked at it and continue to look at it. What does appear to be very workable and quite an exciting possibility is to design materials, so-called metamaterials, that basically are artificial versions of metals that can have a plasma mass that's much smaller than in a natural piece of metal. The simplest idea that occurs to one immediately, once you start thinking along these lines, is, well, instead of using a solid block of metal, just use a bunch of wires with spaces in between. Then the electron density will be much less, as you want. And that turns out to be essentially the winning strategy. Thin wire metamaterials, which are just arrays of thin conducting wires, have a plasma frequency, and for other purposes, they've been designed and used for quite a while. And here's what a prototype axion detector looks like. You just have a bunch of wires in a metal, a bunch of metallic wires. You cool it down, you put it in a very big magnetic field, you instrument it very sensitively, and you got yourself a promising axion detector.
What's the scale of that picture? Centimeters?
It varies depending on the frequency range, but it can be anything from a meter to a few centimeters.
Thank you.
Well, here in fact is a more mature version. So that previous one was an existing prototype that's been built at Berkeley. We have variants of that have been built in Leningrad, where there's a very world cutting edge Metamaterials Institute. And we also have collaborators in Stockholm who built prototypes. So we have several different prototypes of that basic kind. Here's where the prototype that will be the next level of sophistication and polish. And you can see this is the so-called Pathfinder experiment that's been proposed. And the scale is a few tens of centimeters. So all this has to be cooled down and put in a large magnetic field, which limits the volume you can have, but the volume is still very substantial compared to other experiments to search for axions, and enough to do something very powerful, as we'll see, quantify. So as I already indicated, there are theoretical proofs that are fairly definite for what the mass should be, at least in the non-inflationary cosmology of axions. This is designed to show that a lot of work has gone into, by many collaborations around the world, have gone into, and a lot of, both astrophysical, black holes, laboratory experiments. This is a gigantic thing at CERN. And our special purpose detectors, the really different kinds of antennas to look for axions. This is the cosmological predicted band, where you let F float, and this is the coupling as a function of mass. If you ask where are axions providing the dark matter, the mass range estimated in the paper that I just showed you corresponds to this blue thing here. And you see that the existing experiments are either too weak in terms of their detecting power, or in the wrong place to actually home in on that prediction. But this plasma haloscope, this new idea, seems to do it very nicely. So fits the bill very nicely, because, well, here's again that, no, here's the sensitive range that you can make using things that we've already prototyped, and this is the theoretical range of predicted masses here. So we have hope. So the Pathfinder will get you here, and then if that works well, you can scale things up without too much expense to this full experiment. And that's what I wanted to tell you, and I think I've used up my time. So I'd love to give you a chance to ask questions. There are many things I didn't get to talk about. You know, axion physics has been developing for a long time now, more than 40 years. And it's really taken off, I would say, in the last 5 years, where because searches for other kinds of dark matter have come up empty, and more people have come to appreciate the depth of the arguments for axions, and no alternative has appeared for addressing the strong CP problem. It's become one of the real frontiers of research in fundamental science, and I hope I've given you some sense of the ferment there. Thank you.
Thank you, Frank. Thank you very much for this talk. And you stayed in time perfectly because we have to take into account the many minutes that I used up at the beginning.
Right.
So a few questions have accumulated in the chat, and I'm sure that more will come. I see Bernd has raised question. One of them generated a discussion in the chat. Bernd, do you want to continue along this discussion, or do you want to go directly to your second question?
I'd like to go to the second question. Thanks, Frank, for this nice overview of axion physics, although it had to focus on a few topics. My question on the axion heloscope is, in order to be sensitive to different axion masses, do you have to adjust the spacing in the meta lattice?
Yes.
And if so, how do you do that?
Well, you have a bunch of wires, and in the actual designs, there are hundreds or sometimes thousands of those wires. And they're on the thing that seems to be quite effective is you have wires on in frames, so you have planar arrangements, and you have two rigid frameworks, which consist of a bunch of each of them consists of a bunch of planes, large number of planes, each of which contains a large number of wires. That's all rigid, but you move with 1 degree of freedom. You move one of these arrays with respect to the other. That's what seems to work, and that gives you about a 30% range of variation in frequencies.
Quick follow-up question.
So you'll have to sort of cover the whole range, you'll have to build 2 or 3 different detectors, but it looks manageable.
Quick follow-up question. In order to, you'll probably have a trade-off between bandwidths of sensitivity and sensitivity itself. How do you optimize that?
Oh, well, that's a long story that I'm not really competent to talk about, but there are people who are on it, people who are very skilled in data analysis. So there's a question of, how long you spend at different frequencies. Do you tune broadly or narrowly? And you have to, it's a subject that's been studied within the collaboration. This is the alpha collaboration, which is what I've been talking about. But I'm not on top of that aspect. I'm sorry.
Can I use my prerogative here to continue along this line of questioning? Where will you find the strong magnetic fields that this pathfinder will go into?
Oh, well, there are big, strong magnets in many places around the world. They're used in medicine. So we're talking to many potential places. In Fermilab is one. I understand is one potential customer. They or source. They have a large magnet. CERN has many large magnets. The Karolinska Institute in Sweden is a medical facility that has many magnets, and they're always upgrading. So maybe we can get a deal on a used one. And those are big ones because they have to. They put people into them. So and a nice thing about this this design is that we can use solenoids. We don't need dipoles, so we want to be inside a solenoid. That's
thank you. I see another
commercially.
Yeah, thank you. I see another question from Fujang Wang.
Yes, my question is about so we create a high temperature heavy ion quark-gluon plasma in heavy ion collisions, and likely the theta term or theta value or the theta field is non-zero. So what can we do? I mean, what's in your mind that you can think of things that we can do?
Well, understanding QCD better will have some influence on pinning down the parameters of axion physics more precisely. Of course, it'll also, give confidence in the underlying picture, but at this point, I don't think we need more confidence. QCD is right. That's not negotiable anymore. But okay, so as I said, I alluded to, it's not directly experimental, but maybe you could have cross checks of the predictions of lattice gauge theory, which are a necessary component to relating the parameters of the fundamental theory, in particular the value of F, to the observed mass of the axion, or the predicted mass of the axion, because the rough estimate was lambda QCD squared over F, but what you mean exactly by lambda QCD squared is something that is a much more technical and demanding calculation, and that certainly needs work. And there are enough uncertainties in the lattice calculations that it would be very good to have independent checks of their predictions experimentally. So that I think is what could be contributed by experiments and in conjunction with the lattice gauge theory. I'm sorry I can't be more precise about it, but I just haven't put enough thought into it. But there are people who think hard about these things. The other aspect is that is related to that, probably, which is that the heavy ion collisions produce some approximation, some reasonable approximation to conditions in the early universe when the temperature was maybe hundreds of MeV, that are crucial in the evolution of the axion field in the theory. So it would be very good to have checks of the underlying assumptions about matter under those conditions.
Okay.
Okay, thank you.
I see one other question related to heavy ion collisions by Vincenzo Greco. Can you go ahead, please, and ask your question?
So my question at the end is strictly related to the one of Zhang. I was wondering if there is, maybe Frank has not had the time to spend to evaluate it, but if we can expect significant production from the field, the theta-0 value, heavy ion collisions, or from the quark and gluon scattering, that coupled production.
I mean, a lot of axions do get produced, but probably, I mean, I have at various times looked at this, but not very hard because it didn't look very promising. That you don't get enough axions to make it practical to try to detect, unfortunately. I mean, you produce conditions as in the early universe, but in a very, very small volume for a very, very short time. So it can't really compete with the early universe as a source of axions.
So I mean, at the LHC, there are experiments that are trying to detect the neutrinos that are created in a proton-proton collision. But you say the axion problem is orders of magnitude more difficult than this? You make lots of axions, but it's just so hard to detect them that you gave up.
Yeah, I gave up. It's possible I shouldn't have given up, but I did give up. And anyone who wants to look into it, I encourage them to do so. But I would be surprised and somewhat mortified if it turned out that worked out.
Are there any other questions? I don't see any raised hands, and we have run out of comments in the chat. Szabolcs, go ahead.
Thank you very much. So much of this discussion was based on the assumption that axions are created at a few GeV temperature through a misalignment mechanism. But I vaguely remember there was also another.
Well, okay. They're not a few. I mean, it's gigantic. It's,
oh, sorry. Yes. The transition was so, but that was a temperature where axions were actually produced. Anyway, could it be possible that they were created, or at least this transition, Pecceian transition, was occurred before inflation?
Yes. Oh, yes. That was scenario B, which I didn't have time to really discuss. It's definitely possible. And then
what would follow from that?
Well, then you're not supposed to sample different initial displacements, because our whole universe corresponds to one choice of the initial displacement. And that makes it possible to accommodate larger values of F. Remember, the density today is approximately proportional to F, but it's also proportional to sine squared theta zero, if you like, the displacement of the initial angle. And so you can accommodate a large F if we happen to live in a part of the universe where theta started off small. Okay. Different parts of the universe that inflated have different values of theta naught, the initial displacement, and we could happen to live in a place where it started off small, and then you could accommodate larger values of F. That's the other cosmological scenario. That actually is a beautiful model, and as far as I'm concerned, basically the only concrete model we have of how anthropic arguments could be important in or could arise legitimately in physics, because we have a model that's absolutely standard, that we can apply standard techniques of cosmology and particle physics to. And the only thing that changes in these different parts of the universe where the misalignment angle is different is the amount of dark matter that you produce in the form of axions. None of the fundamental laws of physics change, just the amount of dark matter. And so you have very, very different conditions in different parts of the multiverse, if you like, that correspond to different values of this theta zero. But you can actually analyze them because they just amount to having more or less density, dark matter density in the form of axions relative to ordinary matter. And it turns out that if you follow that out, it seems that the larger values of theta zero, if you have a large value of F, so the default expectation for an average value of theta zero would be much, much more axions in dark matter compared to ordinary matter than we observe. We observe about a factor of 6 to 1 in our universe of dark matter to ordinary matter. If it was much larger, however, it would be very difficult for galaxies to condense or to have observers. So you can make anthropic arguments that it's natural in the context of anthropic arguments. If you ask yourself, what would a typical observer see as opposed to what is a typical volume support, it's very natural to have large values of F, but small values of the initial displacement. So that's a viable alternative cosmology.
Thank you. This line of questioning sparked another question from Christopher Blumberg. Chris, can you go ahead?
Yes. Can you hear me?
Yes.
Okay. First of all, thanks for a really nice talk.
Thank you.
I was interested in something that you mentioned earlier on in the talk about anthropic implications of taking a large value for the theta parameter. I'm wondering, are there some non-anthropic consequences of choosing a large theta parameter? For example, would taking a large time reversal asymmetry in QCD, would this spoil agent causation, for example? Would there be other effects?
I'm sorry, spoil what?
Something like agent causation or something. So in other words, instead of thinking about anthropic considerations from the standpoint of the universe's inhabitability, maybe there's implications related to the universe's intelligibility or something like this. Do you have any comments on that?
It's a mind-boggling idea, I guess. So if I understand it correctly, what you're suggesting is, well, I'm going to assume that we're in the framework. Well, we're in the intellectual framework where we agree that mind is an emergent property of matter, comes from brains, and you ask whether brains could operate very, very differently if there were more fundamental time reversal symmetry.
Sure, or I guess maybe
nature.
Yeah, maybe less speculatively, just in the sense of, are there other observable consequences that choosing a very large time reversal asymmetry like this would imply, aside from ruling out?
Well, they seem to be pretty, I have to say, they seem to be pretty obscure, because remember, we're talking about QCD, and that in the natural world, that comes down to properties of atomic nuclei. And the properties of atomic nuclei are pretty well hidden in everyday life, because they're within electron clouds, and chemistry operates almost independently of the details of nuclear structure. Now I know I'm speaking very crudely here, but if there's a path to go from time reversal asymmetry in QCD to sort of macroscopic behavior of matter that would make a difference for everyday life, even if the theta parameter were, I don't know, a 10th, a 5th, one. I think there would be noticeable effects for in nuclear physics, but and maybe T-violation would have been discovered in the early 20th century instead of the late 20th century, but I don't see how it would affect everyday life.
Okay.
Very much, but maybe I'm missing something.
No.
And you'd also, one should also consider possible effects in cosmology and evolution. So there might be more subtle effects along those lines, but I have a hard time seeing it in the context of everyday life. How should I say? If you regard it as a small perturbation on the existing circumstances, I don't see how it gets amplified in any way.
Okay, thank you.
There is another question from Fujang. Let me just quickly read it. So you said that the axions are very light, but you also said at a different point that they are moving non-relativistically very slowly. Why was that?
Yeah. Well, it's because they were produced a long time ago as a condensate cosmologically, and they're subject to something called Hubble friction, which basically is the kinematic effect within general relativity that in an expanding universe, things seem to slow down. That's why things cool, they slow down. And that's what's happened to the axions. I mean, yeah, this can be discussed more precisely, but that's the basic concept. Yeah.
I assume that answers your question, Fujang.
Yes. I was just thinking that the cosmic background is 3 degrees, and that's comparable to the mass that you estimated. But if the axions,
well, photons are a very different story. Photons are a different story because they can't slow down. that's yeah. So
okay, yeah. Thank you.
So we are running up to our time limit, and also I think the stream of questions has ended. So I think this is a good point to thank you very much again for this inspiring talk, and thanks for opening this year's seminar series, which is such a beautiful talk.
Okay, thank you very much. Thanks for the opportunity, and Happy New Year. Happy Year of the Tiger. Okay, bye now.
All right.